Thank you very much for inviting me. I'm happy to be here. I am Gretchen Benedicts. I'm a member of the Space Science and Technology Center, which is over in the School of Earth and Planetary Sciences at Curtin. And I am leading this fabulous team listed here, including Anthony, who was the supervisor of Mitchell, who has done an internship this summer. And what we've been looking at is we're trying to figure out the surface age of Mars. And the way we need to do that is a little complicated. So one thing we need to start with is why would we need to know ages? What does that give us information about? And well, if you're a geologist on Earth, you like to map things, you like to look at a surface, but then you also like to go and get rocks and you bring them back to your lab and you tear them apart and you say, oh, that age is that. So I can now say that that age of that thing is there, and so I know that that occurred then. I can start thinking about, well, how did things move around? People look at Australia and they find bits of material, rocks down in here that are connected to rocks that are in Antarctica. The ages match up when they analyze those, and so what they can do is they can put together the whole plate tectonics thing. Now, we don't have the ability necessarily to do some of that stuff, but basically what we want is we want ages because that gives us an evolution. That gives us a way to track the history to figure out how did this thing happen. So how do we do this for space rocks? Because I'm an astrogeologist, that means I like rocks, but I study rocks from space. Now, well, I've always said that I'm a geologist. I would love to do field work. If I did field work, it would be the most awesome of the field works. However, I have to do sort of remote field work, so I can't go out there into the world. But what we do have is we have meteorites that come to Earth. So there are rocks out in space, they smash into each other. Bits of those rocks fall apart, they come swinging into Earth, we pick them up, mostly in Antarctica, because that's a really nice, easy way to preserve them for a really long time, and we can go find them. But we have about 60,000 meteorites on Earth that we can go and interrogate. We can do all of the things that we do with terrestrial rocks with those, and we can figure out all kinds of ages. We can find out when did they form? When did this rock form? We can find out when was this rock impacted, affected by impact. We can find out how long did it hang out in space before it landed on Earth. We can get all kinds of really cool information. The one thing we cannot do is say, what body did it come from? Where exactly on that body did it come from? And that's a piece of context that would be really helpful, because otherwise we say, oh, here's a rock, and it came from there, and we can tell you everything about this rock, and we know that it tells us a whole lot about the solar system, but we're not 100% sure where exactly in the solar system it came from. So this is one of our chronology issues. However, we can do things. We can find other ways to figure out how old something is, and this is kind of a different way to do it. We can actually look at the surface of a body. So if we look at that surface, we can determine, oh, well, maybe that thing happened before that thing. And we can do that in certain ways, but what we have there is we've got a thing that says, okay, that happened before that, because like any mapping thing, if you've got something on top of another thing, because we know how things generally function, you don't start with something on top and stick something underneath it. So we can kind of say, all right, well, the thing underneath must be older than the thing on top. And so we can start to say that. But if we want to actually say, this rock is this old and this rock is this old, we need a way to calibrate that. So if we can get a sample, we can actually say, oh, well, that rock is this age and that rock is this age, and that can give us a lot more information. So how do we do this? We do it by a process called crater counting. So this is an image of Mars. This is an image of Mars that is a laser altimeter image. So it means that it's measuring, using a laser to measure the height. So the different colors are actually representative of elevation. The blue colors are really deep, and the white colors are really high. And so this is all of Mars, the entire planet. What you can see by looking at this is there's a image underneath the colors that gives you some topography, so you can have a look at that. But what I want you to see and notice about this is that you see a very different kind of structure in the northern hemisphere than the southern hemisphere. And this is something that happens in a lot of bodies. This happens to Earth, but Earth is really, really active, so we don't see the effect of it as often. But a lot of bodies out in space, especially the inner planets, have a lot of craters on them. And that is this whole feature of things are bumping around out in space and they send their bits of rock towards the inner solar system, that hits the surfaces. We can look at a surface and we can say, okay, well, this is pretty awesome. We can see that this is much more cratered than that, so that's going to tell us something. So the way crater counting works is if you have more craters on a surface, it necessarily has to be older because it has to have been around for enough time for those craters to build up in general, okay? So when we first started looking at this when we were going to the moon with the Apollo times. So we had mapped a bunch of the moon, we saw all these craters, we started looking at this and saying, hey, wait a minute, those big darker areas, the mare, they don't have as many craters as those big bright areas, the highlands. They don't have as many craters, they must be younger. And then we actually went to those dark areas, we actually collected rocks, we came back, we dated those rocks in a lab, and all of a sudden we could find a way to create a time frame. So we could say, oh, now we can say, we'll count all these craters on this surface, and we know that that equals this rock, so this line that we get is going to be equal to that age. So this is how we do it. So this is just a very simple visualization of how crater counting would work. So here is time equals 1. Time 0 would be blank. Time equals 1 is you have one really big crater form, because you have one really big piece of material. You have a couple of medium size, and you have a whole bunch of little ones. And this is just a function of if you were to smash a rock on the ground that smashed, you would end up with some big pieces, a few more medium-sized pieces, and a whole bunch of little pieces. It's just the way it works. So when you smash planets together or you smash asteroids together, you're going to get a similar issue. So you're going to get this kind of distribution of crater sizes and impacts. This is time 2. So we've gone along. Now this isn't 100% accurate, but again, this is a simple visualization. We go along in time. We get another couple of big ones. We get a few more of the medium ones, and you have a whole bunch of the small ones. Small ones start overlapping some of the big ones. Some of the big ones will overlap eventually. So you start to see that you're building up more and more of these craters. So the more small craters you have, the younger you are getting, because you've been building up those small craters. Okay, so what happens if you have a lava flow? Lava flow comes along, covers up all of that material. This is a geologic process. It can be a flood, it can be a lava flow, it could be another impact that's giant. But what you have then is you have a fresh surface. So you go to time 4, now you start counting, all right? So this is kind of an interesting, got relative ages. This stuff down here is older, that stuff is younger. Okay, so these are our 4 little areas. How do we get at this age thing? Okay, so what I'm plotting here is diameter, and it's arbitrary units. We usually use kilometers or meters, but you're just going to count up the total number of craters, roughly, at that diameter size. So again, these are just made up numbers, but what you see is this trend. So you see smaller ones, bigger ones. All right, so we go to time 2. Now, in actual fact, time 2 should be under time 1, but that's because I didn't do the model right. I needed to model smaller craters, because the farther along in time you get, you don't have as many of the big ones to make big holes. But what this is showing you is that you're going to get a different line at a different age. So we go here, so we've got a time 3. So this is time 3, and we've got a lava flow that's come in. Now, if we just were to look at everything across that entire field, we'll just get another line that's younger. But what we know is that we can actually differentiate those things if we decide to look at the number of craters on a specific area, not over the entire thing. So if we just look at the craters there versus the craters behind, what you're going to get is you're going to get a slightly different line. So you're going to get what we will call them isochrons. But basically what you're seeing is that this is time 4, just over the entire area. But if we divide that into the 2 different areas, this new surface, which is the younger surface, has a very different, distinct line that's farther away from the older surface. So that means that we can actually differentiate these 2 things. And if we can find a rock that came from that surface, that's really going to help us. This is how we show this. This is in the more complicated version. So these are 3 different ways we can look at it. We can look at, these are crater diameter here and here. This is giving you a rough surface age. So basically you can see that if you look at the crater frequency of 1 kilometer craters, I believe, you can see that this is how it would change over time. The number of that size crater you would get over 4.5 billion years. Okay, so you don't need to remember any of this. Basically what we do is we have these little lines that say this is 4 billion, this is 1 million. If we can count the craters and plot them on there, we can kind of get an age. Here is where supercomputing comes in. So we have an option. One, we can look at the surface. We've sent spacecraft to a bunch of different planets. They've taken lots of different images. We can get a picture. We can start looking at it. We can take a pencil and we can circle all the circles on it. And then we can take a ruler and we can measure each and every one of those circles. And then we can obviously do the scaling by multiplying by whatever your units are. And we can do that. People have done this. People have done this for the entirety of Mars. People have done this for the entirety of the Moon. So for Mars, 385,000 craters counted by hand. That was some person's PhD. You know, at the time, this was what they could do. And it's an awesome, awesome database. It's an amazing way to look at things. But that's down to 1 kilometer in diameter. So if we're looking at trying to get to an age that is younger, so here's 1 kilometer diameter. If we want to get to ages that are less than 1 billion years old, we need to count craters that are less than 1 kilometer in diameter. Okay, so that way. So this guy did it for Mars, 385. He's done it for the Moon, this guy. It's quite impressive. So he's done it for the Moon. He's got like 1 million craters greater than 1 kilometer. And I think the first one took about 6 years to do for Mars. And I think the Moon has taken 6, 8 years to count. So that's cool. But Google or someone invented facial recognition software, and GPUs came along. And so we thought, well, surely there's a way to do this that you can say to a computer, hey, find me those circles, and just count them up. Wouldn't that be easy? That'd be super cool. So that is kind of where we're headed with this. But people started doing this in like the early 2000s. They thought, yeah, let's do it. We'll do it. And they've tried and they've tried. And they've given it a go. But it turns out that until about 2 years ago, the algorithms really weren't friendly enough. It was still really hard to teach a computer what a circle was. Computers are really stupid. They're really stupid. You've got to tell them everything. Everything. So now we have some amazing folks figured out how to tell a computer how to read things faster in an image. So this has been really part of it. So we have applied some of these algorithms. This is what the manual counting database looks like. So this is longitude versus latitude. So this is Mars again, but just the craters. These are just the craters bigger than 1 kilometer in diameter. So this is basically the manually counted database. And what you can see, we can see they're big. We did it so that the symbol size was equivalent to the size of the crater. So we got some really big ones that we can see. But you can see there's a lot of blank areas. So like this area doesn't have a whole lot of stuff on it at all. Just looking at this, we can say relative age. I mean, we could do it by looking at the planet, but we can look at this and go, oh, well, relatively, this is young, this is super young. This area in here is pretty old. There's something happening there. So we got some interesting relative ages we can work with here. But we need to improve that. So we couldn't find a way to do this until now. So we have decided to look at, if you actually take 2 different people and you give them the same data set and you put them in different rooms so they can't interact with each other, and you say, circle all the things, they will come back with 2 different databases. They will come back with about 80% correlation. So pretty much what we have to do is we have to get around 80 to 85% correlation. from an automated version relative to a manual version. So that's what we're aiming for. We used a convolutional neural network, which I recently learned from YouTube is really, really cool. I didn't understand it before. And ours has like 53 layers in it. It's really cool. And so it's really ideal. This convolutional neural network is ideal to apply to images. And what we have coming from Mars right now is images. We have got images, images, images. We have got a global data set of imagery at 5 meters per pixel. The imagery that created this greater than 1 kilometer database is 100 meters per pixel. So this is what we are going to test on. We started here. In 2017, we were working with the Curtin Institute of Computation, and they found this YOLO, you only look once, algorithm that they applied. And it's a really cool one because you can actually you can stick an image in, you give it a training data set to tell it what to look for, and then it will spit out the things that it has found. And it's really good for living things. So the example they show on the web page is that you can have a picture that has a person, a horse, and a dog in it, and you've trained the algorithm to tell the difference between a person, a dog, and a horse, and it will. And it's very cool that it does it. But we thought, well, surely we can say, here are some pictures of some circles that someone else counted long ago, and there's a lot of them, so why don't we use that as a training data set and see what happens? So we did that. But what we really want to do, we tested it and we used the 100 meter per pixel data set. But what we want to do is we want to apply it to the 5 meter per pixel data set. All right, so we needed a training data set. We needed to create a list, a library of comparisons, so that, because it's not unsupervised learning, it's supervised learning, so it needs to have something to learn from. And so we did that. We found, we used the manual database, and we looked at the images and we said, okay, where the manual database says there is a thing, that's great, we're gonna confirm that. We did that for, we had 6,384 images initially, but then we cleaned them all up, so that brought us down to 1,200 images. But that gave us, we had to actually go one more step, and we had to get another, on top of the cleaned annotations, we took it down one more, and we ended up with 947 images, which ended up with around 889 craters. Is that it? Roughly. But if you take an image and it has cleaned craters on it, and then you rotate it several times, you expand what the computer can learn from. So the computer can learn that this thing is a crater, whether the shadow is here, or it looks like it's, you know, upside down, or so that is how we created it. So we've got a database that's actually pretty good. And it's probably the best database of a training database. So up to now, the previous one to this, I think, had 24 craters in total, and so ours is thousands of craters. So it's a good database. So yeah, we ended up with this. So we used those images, 2,490 images. We did it for 40,000 iterations. We had these learning rate things. This is where I go off the rails because this becomes computing, and I'm like, there's some loss and some things. But what we did was we had created this total set. We had cleaned up these things. So we trained off of 2/3 of it, and then we validated off of the last third. So we put that last third of cleaned up images through as unknowns to see, can you find the things we think you should be finding? And it ended up with 90% recall. 90% recall is actually, 94% recall, which is better than the 85% we were aiming for. So that meant that, oh, well, we've got a pretty good algorithm here. So I forgot to put the animations in so you could see things that are, you know, so the big reveal, which would be great. So the way this pipeline works, the workflow is that we would put in an image, and the image is about 26,000 by 17,000 pixels. So it's a pretty big image, 100 meters per pixel. So it's about 2,600 kilometers across. When we first ran it, it took 3 minutes to crop that image into 960 by 960 tiles. So it takes that full image and crops it into tiles that are 960 by 960 pixels. That then is run through the algorithm, the YOLO algorithm, with some things, and that used to take 2 minutes. So it would run it on the cropped images, but that's on the GPU. If you try to run this detection on a CPU, time expands and it takes much, much longer. And then finally, the biggest problem, or the biggest part of the whole pipeline at the time, it took 10 whole minutes, was that it had to take all of those images that had been detected and then put the annotations onto the detected tiles and then merge the tiles back together, mosaic them back together into the full resolution image. So that took a long time. But we figured out that if you don't start with a PNG, if you start with a JPEG, it goes a lot faster. So we went from 15 minutes to about 2 minutes to do a single 26,000 by 17,000 image. So we did that on everything. This is a very blurry version, but what we've got here is we've got the red and the blue are the manual versus the computer automation. And you can see there are differences, but they're not hugely different. So we're going to go here where we can see a little better because it's better, higher resolution. So you can see that there are some areas where, so blue is manual, red is automatic. So you can see there are areas where we missed something. And if you look at that ground back there, that would be kind of it is a crater, but it's very degraded. And what our database or what our algorithm is trained on is not degraded craters. So we picked really nice fresh craters for the most part of a variety of sizes. So what we can do is we can keep refining that training database, and we can add in levels of degradation. We can add in slightly different shapes. Most impacts are pretty circular, but not all of them. And so this is it gives you a feel for how close we are. But then there's things like that, where if you look at that, I can't see that being a crater, but there's some circularity down here. But so there are areas where the manual database might not have it right either. So making that one-to-one comparison isn't necessarily going to be, the manual database isn't necessarily 100% correct. So that's kind of a close-up. And so one of the other differences we get, but again, it's not massive, is the size of the crater. So you can see that the circles might be centered properly. Like this thing here is another one of these phantom craters. But you can see that our sizes and the manual sizes can be a little bit different sometimes. And that's also down to the training database. What this is showing you is that the smaller we go, when we're hitting the resolution limit, is when our errors are going to get larger. But we can fix that because we can put in higher resolution imagery, or we can degrade imagery to kind of get rid of some of that. So this is a comparison. Oh, sorry, I just slammed the microphone. So this is a comparison across the entire surface of Mars. So this is the plot, and what we've done here is we're doing a crater density. So the color in here is we counted up the number of craters in a given area, and we put it into a grid of 100 kilometers square. So each square is 100 kilometers square. So each little pixel in there is like that. And what the different colors show you is that the yellow, it has more craters in it, and the black has fewer craters in it. So that's showing you in general what the crater density looks like, which you can roughly tie to older or younger. But what we wanted to do is we wanted to see how do those two compare. So when you have these images like this, you can subtract them and figure out where the biggest differences are. And so when we did that, we found that the biggest differences where we don't match the manual database are very much defined by certain areas. And then we can explain those away because there are certain things that happen on the surface of Mars that mean when we are looking at images that are above and below 45 degrees of latitude, the projection of the map becomes a little bit wonky. So you might not get circles, you might get elongate things. And where we find So it might not be finding things as well there. And where we find things where we're finding more than the manual, sometimes that's related to the fact that there's an effect that happens when an impact occurs and it's big enough, it will splash material out from the surface, and that material will come back down and it'll be moving fast enough to make new craters. We call those secondary craters. So you have to be able to account for those in order to interpret the age properly. So some of these areas where we have a lot of red is where there were big impacts that actually left a lot of these secondary craters that aren't part of a primary fall. This lets us look at how these compare. And so overall for this diameter range, so we got 1.5 to 10 kilometers. And this is the diameter range that works best for the Themis, which is the 100 meters per pixel resolution. This diameter range works best because we trained on circles that were 10 to 100 pixels across. And so when you convert that, you get to this. But basically, this is just showing the difference between them. And so we have a little bit more of a difference over these slightly larger, but we have really good agreement at the smaller ends. And that's really, really good because that's what YOLO is built to do. YOLO version 3 is built to look at small things really well. So that was part of the algorithm. Okay, so we've got a little bit of testing. So the way we test this is, okay, what we want to do is figure out ages. So what has happened in the past with cratering algorithms is that they've said, okay, we've got this cratering algorithm, let's run it. But very few people have actually said, let's take the results of that algorithm and actually determine ages over the same areas that have been measured before and see if it actually works. So we've done that, and Anthony is the guru of this. And so what we've done is we've taken a quadrangle. This one is a specific area of the surface of Mars. And in green is our results, and in red is the results from the manual database. And the fact that we're getting numbers that are right in the same lines is really good. That means that we're in the right ballpark. We're crossing all of the same isochrons. And then we can figure out where our differences are, but what that is telling us that we're in the right ballpark. So we're not getting like way more or way less. And that's important. Because the other thing is, if you look at the difference in ages of these isochrons, you have to go, if you're really far away, you're going to be billions of years off, right? So a little bit of difference is actually not a big deal, because you're looking at things that are differences of a billion years. But if we can get to 10 million years or even 1 million years of difference, that's going to be amazing. We tested it at some areas that have the rover. So this is where the Mars Science Laboratory Curiosity rover is. It's called Gusev Crater. And wait, is that right? Yeah. Gale Crater was the other one. Yeah. Okay. Yeah. So this is where MSL is. And so they have done a whole bunch of counting. And so we compared our counts to their counts, and we find that we have good overlap where the areas were the same. So we used our Themis, our 100 meter per pixel data set, but we were comparing over things that have much higher resolutions. So CTX and CTX is 5 meters per pixel, and HiRISE is can go down to 30 centimeters per pixel. So it's a much higher resolution. But we're finding good agreement in those areas as well. And we tested 4 different areas, and we got within error on all of them. So right, we got 3.64, they got 3.65, we got 2.99, they got 2.89, 3.58, 3.58. So the algorithm is performing well. We like it. This is an area called Jezero Crater, and this is where the Mars 2020 lander is going to go. So this is the one that's going to launch this year, land early next year. And the crater is here. This is a higher resolution, so this is 5 meters per pixel resolution. And we mosaicked this together, and we thought, well, let's give this a go. The reason they're going to this area is because of this feature here. That feature there looks a lot like a delta. So as a geologist, you're going, oh, water, great. That's how you form deltas. And one of our big things about Mars is, where's the water? Where did it go? Why is it not there anymore? Because we see all these really interesting features that say water. So this is a really interesting feature. So we've applied our thing. One thing that we want to do is figure out, well, how old are these different areas in this region? So what this is showing is the difference between the different resolutions and the numbers of craters we can get, which means the ages we could actually get. So this is at 100 meters per pixel. We counted 8,216 craters on that whole image. Within this one little square, we counted 112 at that resolution. If we take that square out and we do it at the next higher resolution, we go from 112 craters that are bigger than 1 kilometer to 3,825 craters that are bigger than 100 meters. That's getting us to we're getting into some higher resolution. Now that still doesn't get us into the crater. So here's the crater. We want to go into the crater. So at this resolution, we count 29 craters that are bigger than 100 meters. If we go to the next level of resolution, we get 1,078 craters in that same region. So this is letting us really take that resolution and say, okay, the more craters we can get at these smaller sizes, we're going to be able to get really interesting ages off of this, which we have then subsequently applied. Oh, and this is where Costa comes in, because Costa created the training database to deal with HiRISE, the really high resolution data. This CTX, the 5 meters per pixel, we just applied the algorithm with the training database we had from the 100 meter per pixel, and that was okay. It didn't actually need to be too retrained, found circles. But when you get to this level, there's a whole bunch of detail that the computer just says, yeah, no, I can't use what you did before. So Costa did all the retraining, and then we were able to get this. So now we can pull out an age from this area, which is actually off here somewhere. And that lets us, this is going to help us to feed into some of the interesting science that's going to be done there, because what they want to do, the mission is all about collecting samples, finding samples that are important, that are going to tell us about water in that area, and then caching those samples to be picked up at a later date. So this is going to help, because we're going to be able to say, actually, here are some really interesting regions, because we can figure out their ages now. So that's really good. Okay, so like I said, we kind of applied it to some individual images of CTX data. This is the original 100 meters per pixel data set. We've now run it for CTX, the 5 meters per pixel data set. Again, the algorithm just operated on its own. And what happens is we get a completely different picture of Mars. This is literally an image of every dot on that is a crater. So we're seeing some really interesting morphologies in this that we hadn't seen before. So if we go back to here and we say, okay, look, there's nothing happening in here, but we go here, there's a lot of stuff happening. And what's really interesting is we're seeing some really interesting streaky bits that have been noticed before, but not to the extent of what we can see. And just so you know, this is 384,000 craters between 65 and 65. This is 17 million craters. This took 2 months to count. The previous one took 6 years to count. Well, it took us less than 6 years when we repeated it. But so this is greater than 40 meters. We have brought down the number of craters you can count on the surface of Mars, orders of magnitude. We're now in the process of going into these very specific regions, like this one here. This is what it looks like at 100 meters per pixel, and this is what it looks like at 5 meters per pixel. So what we're seeing is we can actually see this information about, okay, the crater hit here. We can see that it's that crater. But what's really interesting is these streaks are very clearly related to that crater. And what we didn't know is that these streaks go to here. They used to, we used to say they might have come out to here. Now we know that crater streak is going out to there. We're going to be able to take this information and start feeding it into understanding the impact that happened. The impact looks like it was oblique. We might be able to figure out how fast it was going. We might be able to figure out how big it was. We might be able to figure out, how did it splash that much material. So, thank you. This is what we're working on. machine learning, GPUs, yay. Thanks. I didn't do it. I just talk about it.
Well, look, I was excited to read the sort of preview and to see the presentation and to get the sort of level of excitement and insights. Fantastic. I don't know. Do you want a question or two?
I'll take questions. That's fine. If there's any. Yeah.
So it's my understanding that Mars has been geologically inactive for quite a long period of time, or at least in terms of anything close to plate tectonics. So really what you're looking at here is erosion due to wind and liquid on the surface.
That would be very recent history, erosional history. The meteorites we have in hand tell us that there was active volcanism 150 million years ago. So it's possible that there is active volcanism now and we can't see it because our resolution isn't high enough and we're not seeing hot spots that way. And it may not be erupting onto the surface. But this is another thing that we're going to be able to do, is to actually try and define where on Mars did the meteorites that we have come from. Because we know how old they are, we know when they formed, we know when they got launched, we know how long they were in space. So that gives us this whole range of things that we can say, okay, we know how they formed 150 million years ago. Go find the surface that's 150 million years. We know from impact modeling that any crater bigger than 3 kilometers is going to be energetic enough. Any crater that has formed that's 3 kilometers, the impact would have been energetic enough to launch material into space. So let's find a 3 kilometer or bigger crater that is the age of what we know was the launch point. So we can take all of this data together and try to figure out where are the specific craters, and then that's going to kind of open up, oh, we know that volcanism was active 150 million years ago, right here.
Thanks.
Early on, you said there were some like 60,000 asteroids, individual ones here on Earth.
60,000 meteorites, yeah.
Right, and given that you can extract so much information from each individual one,
yeah.
Is there a correlation between them? Like you can say, well, gee, this origin of this one must have been the same as the origin of that one.
Yeah, absolutely. So what I didn't say is we have 60,000 meteorites on Earth. They sample mostly asteroids, and mostly about 20 asteroids or 20 rough compositions. They sample the moon and they sample Mars. But of the 60,000, about 200 come from Mars and about 150 come from the moon. And the 150 that we're calling meteorites from the moon are not the Apollo samples. Those are meteorites that got knocked off the moon by impacts and came to Earth on their own. We didn't bring them back. So the Apollo samples are on top of that. But it does mean we do have the ability to put these all into categories compositionally. A lot of the times, we don't know what body they come from, but this is where the Desert Fireball Network is helping out. Because if we can track orbits down to the ground and out into space, that's going to help us. And if we've got the rock on the ground, we can use all that compositional information to track back into space. But there was another thing I was going to say that just went away. But yeah, so basically so we know that these 200 come from Mars, but they probably come from maybe 10 craters. So they're not from all over, they're from very specific areas.
It's just awesome, it's really exciting and fantastic to see. So thank you again, and look, fantastic, so thank you.
Thanks. Thank you.